on primary side. As you know, this core is made up of iron. Okay, so it is a ferromagnetic material. So what I am doing is I am connecting a wire in a form of coil, and it will have, let it have NP number of turns. Now VP is the primary voltage or sending end voltage. VP is the primary voltage or secondary, sorry, supply voltage, and IP is the primary current, and IP is the primary current. Now on the secondary side, I will have one more winding called, this is called secondary winding. Okay, secondary winding, and this secondary winding has ns number of turns, has ns number of turns. Okay, so this is Vs, let it be Is, let it be Is. So the principle of operation can be explained with the help of Faraday's laws of electromagnetic induction. Let, when IP is passed through this winding, what will happen? Flux is created in the winding, and this flux will have a path or will complete its path through this core. Through this core, the flux is completing its path. Okay, because this core will offer less reluctance to the flow of flux. Let phi is the flux created. Okay, so this phi, which is created by this NP number of turns because of current IP, is linking with the NS number of turns. Is linking with the NS number of turns, and according to Faraday's laws, when a flux links with conductor, EMF is induced. Let us call it as E2. Let us call it as E2. See here, suppose this is the flow of flux, path direction, and the same flux is again coming back and interacting with the NP number of turns. And according to Faraday's laws of electromagnetic induction, if flux interacts with turns, again EMF is induced. So E1 is EMF induced in the primary side. Okay, EMF induced in the primary side. That means what is E1? E1 is EMF induced. Okay, EMF induced in primary winding. Okay, so there is a difference between VP and E1. What is VP? VP is the supply voltage or primary side voltage. It is the supply voltage. Okay, the voltage which you are supplying to this transformer. Okay, and what is VS? VS is terminal voltage. VS is terminal voltage. Okay, terminal voltage. Now what is E2? E2 is EMF induced in secondary winding. Okay, there is a difference between VP and E1 and VS and E2. And in a practical transformer, E1 is not equal to VP. Okay, and E2 is not equal to VS. Okay, in a practical transformer. Now, so we are now deriving the expression for E1 and E2, not VP and VS. Okay, so E1 is the voltage induced in the primary side. Now, if I want to know what is the amount of E1 and E2 induced in the both the windings, what I'm going to do is I'm going to take the Faraday's laws. So according to Faraday's laws, E1 is equal to the number of turns on the primary side into rate of change of flux. Rate of change of flux. So let the flux that is flowing in the core is phi m sin omega t. Phi m sin omega t. Why the flux is a sine wave? Because Vp is equal to Vm sin omega t. I am giving a sinusoidal voltage as input. Okay, sinusoidal voltage as input, and Ip is the current that is flowing in the primary side, and this will also have a sinusoidal shape. Since Ip is creating the flux phi, so the flux phi will also have the same shape as Ip. That is why I am taking phi is equal to phi m sin omega t. Now, if I substitute this phi in this equation, E1 is equal to Np into d by dt of phi m sin omega t, So what happened now? If I derive this is Np into phi m is constant, so bring it outside. So derivative of sin omega t is omega into cos omega t. Okay, cos omega t. So E1 is equal to, what is omega? 2 pi f. Okay, Np phi m cos omega t. Np phi m cos omega t. So this is the EMF equation. Of the primary side. Now, what we have derived, I am writing it again. E1 is equal to 2 into pi into f into phi m into cos omega t. So this is in the form E1 is equal to Em cos omega t, right? Em cos omega t. What I can do is, I will write E1 is equal to Em into cos omega t. I can write it as sin omega t minus pi by 2. Sin omega t minus pi by 2 is cos omega t. Now it is in the form V is equal to Vm sin omega t. For a sinusoidal wave, the RMS, Vrms is equal to Vm by root 2. Similarly, if I want to find the RMS value of this above voltage of the equation number 1, ERMS is equal to Em by root 2. What is Em? E1, I will write E1 RMS. E1 RMS is equal to, what is Em? 2 pi f phi m into, sorry, here I have missed Np, right? Here I have to write Np. Np I have missed. So here into Np. So here. So what is Em into Np? Okay. 2 pi f phi m Np. Okay. Into by root 2. So E1 is equal to root 2 pi f phi m into Np. What is root 2 into pi? What is root 2 into pi? If you multiply root 2 into pi, you are going to get 4.44 into f phi m into Np. Then what is this f? F is the supply frequency. So what is the supply here? Supply frequency. What is the supply here? Vp is the supply voltage. So the frequency f is nothing but the frequency of the voltage. okay, which you are giving to the transformer. Now the E1, that is the EMF induced on the primary side, RMS value is 4.44 F pi m into NP. Okay, similarly, we can write the EMF equation on the secondary side as 4.44 F pi m. If you do the same calculations, okay, into, but here we will get NS because we are going to use, so E2 is equal to NS into d phi by dt. Okay, but in an, so what is phi? Phi is equal to pi m sin omega t only we are using. Why? Because in a transformer, the flux is constant. The flux is constant. So if you substitute this one, then you are going to get 4.44 F phi m ns. So this is the EMF equation of the transformer for primary side and secondary side. Okay. So now we are successful in deriving the EMF equation of the transformer. Is it clear up to now? Is it clear? Please respond now. Suppose this is your transformer, and for this transformer, what we have done? We have wound two windings. We have wound two windings. One is called primary winding, and second one is called secondary winding. Suppose this is your primary winding. Okay, and what is the voltage you have applied to this primary winding? The voltage you applied is Vp. Okay, where Vp is equal to, what is Vp? Vp is equal to Vm sin omega t. Sin omega t. Okay, when we apply this voltage to this primary side, IP starts flowing. IP starts flowing, and this IP is creating an voltage called E1. This IP is creating a voltage called E1. What is E1? E1 is equal to EM, which you have derived, right? Sin omega t minus pi by 2. Omega t minus pi by 2. That means the primary voltage and the induced voltage are having how much angle difference? Pi by 2. That means suppose this is the EMF or IP. Okay, IP. So this is the pure inductor. Let us consider this as a pure inductor. Okay, the primary winding with NP number of turns is a pure inductor. This is primary side, right? The primary winding is a pure inductor. Okay, in a pure inductor, what is the relationship between voltage and current? What is the relationship between voltage and current? Suppose this is the voltage, okay, Vp, you are applying, and this is the current, right? This is the current. Current lags voltage by an angle 90 degrees in a pure inductor. Current lags. So you are applying Vp and Ip to this inductor. So the Ip will be lagging Vp by an angle 90 degrees. Suppose if I take Ip as reference, then this will be your so what would be your Vp? So where should I write this Vp? So this is your Vp, right? So this is your Vp. Okay. So this is your Vp. Now this is your Vp. Okay. Now Now the EMF induced in this is because of this current, and this current is because of this phi. Okay, the current is responsible for creating the phi. So we derived this E1 with respect to phi, right? With respect to phi, it is lagging 90 degrees. It is lagging 90 degrees. That means with respect to phi, your E1 is lagging 90 degrees. Okay, E1 is lagging 90 degrees. So that is represented like this. So this is your E1. This is your E1. So what is the angle between E1 and VP? That is the, what is VP? VP is your voltage which you have applied. VP is the voltage applied, and E1 is the EMF induced. What is the angle between the voltage applied and the EMF induced is 180 degrees. Is 180 degrees. Did you understand how I drawn this vector diagram? So IP is a vector, phi is a vector, and with respect to phi, your E1 is lagging by an angle 90 degrees. Okay, already VP is lagging IP by an angle 90 degrees. Okay. So this is the representation, vector representation of the transformer on primary side. So see here, all are primary side quantities. All are primary side quantities. Now, if I derive the expression for E2, so E2 is equal to the same. E2 is equal to since the same phi is interacting with E2, so E2 is equal to EM sine omega t minus pi by 2. Omega t minus pi by 2. Okay, but the magnitude may change, but the direction is same. Okay, so E1 sine omega t minus pi by 2. See here, by comparing these two, E1 and here EM, EM. Okay, so the magnitudes are different. Suppose it is EM2, this is EM1, where EM2 is equal to 4.44 pi F NP. Okay, sorry, F NS. Okay, and what is EM1? EM1 is 4.44 pi F NP. So E1 is not, EM1 is not equal to EM2, but the E2 which is induced because of the flux phi 2 on the secondary side will also have the same orientation as if E1 okay, as if E1. Why? Because we are representing with respect to phi. That's why this is your E2. So this is E2 and this is your E1. Okay, this is E2 and this is your E1. So both will have the same direction. But the magnitudes may differ because of NP and NS are not equal. NP and NS are not equal. Okay. Since this is not equal, we are going to have E1 and E2. Okay, lagging 90 degrees behind phi, and EP is your